Assignment 5, expected example. Let V be the vector space of all real symmetric matrices over the field R. Now, what is a real symmetric matrix? Suppose you are having a matrix A, and if you take the transpose of that matrix, then that will be equal to again A. Such kind of matrix is a real symmetric matrix. For example, I'm taking the matrix as A, B, B, C. If I take the transpose of this matrix, I will get back again this. Okay, what is the transpose? This is A, then this B comes here, B, and this B over this. So the transpose of this matrix is again A, B, B, C, which is again A. So such kind of matrices are real symmetric matrices. I hope you all know how to take the transpose of a matrix. So here the vector space V is of all the real symmetric matrices over the field R, and we have to show that these given matrices forms the basis for V. Now already matrices are given to us. We have to show that these forms the basis for V, which means we have to show that first thing, that every element of V is a linear combination of these matrices. Secondly, we have to show that these matrices are linearly independent. So let's start with the solution. By hypothesis, the vector space V is equal to. Now what kind of the matrices are present in vector space V? It is real symmetric matrix. So I'm writing A, B, B, C, where A, B, C belongs to the real numbers because field is given to be R. So let's take one element from the vector space. So I'm taking again this A, B, B, C because vector space is the element present in vector space is matrix. So I have to take one matrix from vector space V. Now because I need to show that every element of V is a linear combination of these matrices which is given to us, so I'm writing this element A, B, B, C, that is equal to the linear combinations. So I'm taking the scalars like alpha 1, 5, 5, 2 plus beta 2, 1, 1, 3 plus gamma 4, negative 2, negative 2, 6. Now when can I say that this element is a linear combination of these matrices? If the scalars alpha, beta, gamma are written in terms of A, B, C. Because the element present in this matrices are A, B, C, which belongs to the real numbers, right? So I must have alpha, beta, gamma to be written in terms of A, B, C. So let's solve this further. So this will become then on adding, just multiply alpha with these elements and beta with these and gamma with these and then sum up all and you will get one matrix. So this is A, B, B, C. If you multiply alpha and beta, gamma with the respective matrices and add them all, you will get your, you will get the first element to be as alpha plus 2 beta plus 4 gamma. And the second element is 5 alpha plus beta minus 2 gamma. And then you will get 5 alpha plus beta minus 2 gamma, same. And then you get 2 alpha plus 3 beta plus 6 gamma. Right, and now just equate the respective elements. A is equal to alpha plus 2 beta plus 4 gamma. B is equal to 5 alpha plus beta minus 2 gamma. Then again I'm having B, the same equation. And then C is equal to 2 alpha plus 3 beta plus 6 gamma. So we are having these three equations. Just solve these three equations and you will get alpha, beta, gamma in terms of A, B, C. When you solve these, you will get alpha to be equal to, on solving these three equations, we get alpha to be equal to minus 3a plus 2c, and beta is equal to 1 by 2 of 17a plus b minus 11c, and gamma is equal to 1/4 of minus 13a minus b plus 9c. So you get alpha, beta, gamma now in terms of A, B, C. Just putting these values of alpha, beta, gamma over here in equation 1. So we get, I'm putting the value of alpha with this, I'm getting minus 3a plus 2c. Then put the value of beta, half 17a plus b minus 11c. And then putting the value of gamma is 1/4 minus 13a minus b plus 9c. So now I can say that this A, B, C, D matrix is a linear combinations of the given matrix, as all the scalars are now in the form of, now represented in the form in terms of A, B, C, right? So therefore, but this A, B, C, D, this was arbitrary, which means every element of V is a linear combinations of given matrices, which means thus V is generated by these given matrices, right? First step is okay. Now the second step is to show that these matrices are linearly independent. For that we need to take again the linear combinations of these matrices to be equal to the 0 matrix, and we have to show that all the scalars are 0. So now taking the linear combinations of the matrices, I'm taking alpha 1 5 5 2 plus beta 2 1 1 3 plus gamma 4 negative 2 negative 2 6 is equal to 0 matrix, right? Then just multiply alpha, beta, gamma with the matrices and add the elements. You will get alpha plus 2 beta plus 4 gamma, and the second element is 5 alpha plus beta minus 2 gamma, and then you get 5 alpha plus beta minus 2 gamma, and then 2 alpha plus 3 beta plus 6 gamma. So this is equal to 0 matrix. Equating the respective elements, we get alpha plus 2 beta plus 4 gamma equal to 0. 5 alpha plus beta minus 2 gamma equal to 0. 2 alpha plus 3 beta plus 6 gamma equal to 0. This is already equal, right? Now we get these three equations, the homogeneous equations. We say this as system, the homogeneous system of equations. Either you solve these equations and get the values of alpha, beta, gamma to be equal to 0 0 0, or there is another way. Just take the coefficient matrix of the system. So you get, taking the coefficients 1 5 2 2 1 3 4 negative 2 6. So this is the coefficient matrix of this given system. Take the determinant of this matrix. If the determinant comes out to be non-zero, then we have the system, the systems of equations will be having a trivial solution, and for trivial solutions all alpha, beta, gammas are equal to 0. And if the determinant is 0, then the solution is non-trivial, and then at least one of them is non-zero. But for linearly independent, we need all the scalars to be 0. For that, we need a trivial solution, and for that, determinant should be non-zero. So let's check what is the determinant for A. It should comes out to be non-zero. So when you solve this matrix, the determinant, you will get the determinant as, alright, this is 1, this is 6, and this is minus 6, that is 6 plus 6. And then we have minus 2, and then this 30 plus 4. And then at the last 4 into, this is 15 minus 2. So which is equal to, this is negative 4. Alright, the determinant of A is non-zero, which means the system has trivial solution, right? It has only the trivial solution. For the trivial solution, thus alpha, beta, gamma is 0. This is a result. Hence, the given matrices are linearly independent because all scalars are coming out to be equal to 0. And if the determinant is 0, then the solution is non-trivial and at least one of these scalars will be non-zero. So that we don't require. That is the case for the linearly dependent vectors. So for linearly independent, we need all scalars to be 0, and for that we must have trivial solution, and for that determinant should be non-zero. Just take the coefficient matrix, or the other way, just solve these three equations and get the values of alpha, beta, gamma, which always comes out to be 0 for linearly independent vectors or matrices. Now hence the given matrices are really linearly independent. So from 1 and 2, 1 is what? That V is, every element of V is a linear combinations of these matrices, and secondly, the given matrices are linearly independent. So from these two, from 1 and 2, we say that all these matrices is a basis for V. They form the basis for V. Alright, thank you friends. Goodbye.